Welcome. I put together a video today to go over some of the important differences between free fall and vertical throwing, when to use which equation, how to know, and how similar and different problems with these two concepts actually are. I also realized that some people cannot access the notes that I put up in Schoology unless you have PowerPoint downloaded on your computer, and you may not be able to see all of the markings that I've made, so this will provide an excellent sample problem for you to reference in case you were not able to see those. So let's start basic. Gravity is a constant acceleration that all objects experience while on Earth. Technically, all very large, very massive objects have their own gravity. All objects have their own gravity, but very massive objects are big enough to have a measurable gravity. Things like stars and planets will have a gravity that you can really measure. Since we live on Earth and most of our experiences will be on Earth, we're going to assume that most of the work that we do in this class is going to take place on planet Earth. So it's worth knowing that the gravity for planet Earth is negative 9.8 meters per second. The negative means down. Meters per second squared means it's in acceleration. And then the 9.8 is just the value. You just have to know this number. And this number is going to be a constant. So if we are ever using equations that deal with gravity, understand that that negative 9.8 meters per second squared is not going to change because gravity does not change. Gravity pulls on all objects with the same acceleration. And if there's no air resistance, all objects will fall in the same way. So it doesn't matter if it's a bowling ball or a tennis ball or a piano. If you drop them and there's no air resistance, and in this class we're not going to worry about air resistance, they will fall and accelerate the exact same way. You could fill out a free fall chart for a tennis ball or a bowling ball and it won't matter. It will be the same because you ignore air resistance and all that's left is gravity pulling them in the exact same way. And since gravity is an acceleration, it will need the acceleration equations. So that's gravity. And then after gravity, we talked about free fall. And then after free fall, we did the kinematic equations to talk about vertical throwing. But let's think about it in terms of gravity. If you did not get these equations earlier, it is essential that you get them now. Because the V0 equals 0, you can use what I called the from rest acceleration equations. And that makes sense. If something's in free fall, it's falling from rest. These are the free fall equations. However, free fall simply means you hold an object up and you drop it to the ground. That's essentially what a free fall is. You don't throw it, you don't push it, you just let it fall. And if you let it fall, it starts off at rest. The initial velocity is at rest. However, if you throw something vertically, that means you're imparting a force, you're imparting a speed in it, and as it leaves your hand, it's already moving. You cannot say that the initial velocity is 0. So, in fact, the initial velocity is not 0. And since the initial velocity is not 0, we have to use the kinematic equations. Please take the time, if you are going to write these down, to copy them correctly. Please notice which exponents have a square. Please don't mix up your V and V0. These are the equations that we're going to use. We have the free fall equations on the left and the vertical throwing equations on the right. As you can tell, All the vertical throwing equations have the v0 term in it. It's not canceled out. The free fall equations are assuming that the v0 is 0 and that term is just canceled out. But if you do not have these equations, now would be a great time to pause it and get them in your notes. So what is free fall? A free fall, as I said, is just simply when an object is dropped and only gravity acts on it. So we're not going to concern ourselves with things like air resistance. So if in a free fall, and I can't stress this enough, before you let go of the object, it's not moving and it hasn't gone anywhere. It always starts with a double zero at the top of a chart. All free falls will always start with a double zero at the top of the chart. Okay. You let go of it, and only gravity acts on it. And unless you say otherwise, I think it's completely fair to assume that you are on planet Earth. So gravity is going to pull it down negative 9.8. Every second it falls, its velocity is going to change by negative 9.8. So all I'm doing is adding negative 9.8 to every single velocity. Because negative 9.8 is the acceleration, that's how much the velocity changes every second. You just keep adding the gravity. The gravity is negative 9.8, and that's how much the velocity changes. However, if you don't like that, please understand that this is also an equation that you can use. You can use that to solve for any of these. The A will always be negative 9.8, and you will just plug the time that you're looking for in. So you want the velocity at 3 seconds, negative 9.8 times 3, gravity times time, bam, negative 29.4. Okay, that's not so bad. And again, because it's a free fall, and now we're looking for distance over here, we're going to use the distance equation. And I can't stress this enough. Gravity never changes. Resist the temptation to use the velocities that you just solved for in this equation. There is no velocity term in this equation. This is the equation that you're going to use to solve for the distances. Well, how is that going to work? Well, I'll show you. D equals 1/2 negative 9.8 t squared. Wait a minute. Bizzuto, why did you write it like that? Because every single time you do this equation, it's always, the gravity is always going to be negative 9.8. Because we're on Earth, and the Earth's gravity never changes. Half of negative 9.8 is in fact always going to be negative 4.9. So look at what I'm going to do. Look at what I'm going to do, and I'm going to try to make it a little bit simple. If you just want to plug into this equation every time you can, but I want you to understand that once you take half of gravity, it's just going to be that number times t squared. What do you mean? Negative 4.9 for 1 second, 1 squared. Negative 4.9 times 2 seconds. But, careful, you have to square the time. Negative 4.9 times 2 squared, or negative 4.9 times 4. D equals negative 4.9. This is what I was encouraging you to do when I was telling you to copy and paste when doing these problems before. I want you to recognize that the gravity doesn't change. And by copying and pasting, you won't be tempted to change the gravity. The only thing in both of these charts, free fall and vertical throwing, that changes is the time. The gravity, the acceleration, the initial velocities all those stay constant. So if I plug those numbers in, it's pretty simple. Here is a free fall chart for planet Earth. Done. Now, what if you were to throw an object straight up and it's caught as it returns? So if a ball is thrown plus 19.6 meters per second on planet Earth, okay. Well, unlike free fall, the initial velocity is not going to be 0. The initial velocity is going to be the speed in which the object is thrown. You also may have noticed that I don't use the word distance anymore. I'm now using the word displacement. We'll see why we do that in just a second. But again, I think whether it be distance or displacement, I think it's safe to assume that it will always start off at 0 before the object really goes anywhere at time 0. Time 0 simply just means the moment you hit the stopwatch. So if I want to time how long the ball's in the air, I'm going to hit the stopwatch the last moment the ball is in your hand. So it's technically 0 meters away from your hand. Okay. Now, I said for velocity that because we're on planet Earth, gravity is negative 9.8. All I'm going to do is subtract 9.8 from the velocity every time, because that's the acceleration that it experiences. So 19.6 minus 9.8 is 9.8. 9.8 minus 9.8 is 0. 0 plus negative 9.8 is negative 9.8. And then negative 19.6. Patterns, patterns, patterns. But if you don't like that, if you're the type of person who says, give me an equation, I feel safer with the equations. I feel like I'll mess up the patterns. Well then, use the vertical throwing equation. Use the vertical throwing equation. V equals V naught plus AT. That would work for any of these seconds. And understand that when you use that equation, the V naught remains constant. The V naught will always be 19.6. It never changes. The A will remain constant. It will always be negative 9.8. The only thing that ever changes in this equation is going to be the time. And the same thing is true with the displacement equation, or the V naught distance equation. D equals V naught T plus 1/2 A T squared. When you use this equation, there are a lot of mistakes that students make, so I'm going to highlight them now. The V naught is the initial velocity, and it never changes. It never changes per problem. Once you know what the initial velocity is for your problem, that is always going to be your V naught for everything that you do. The A is gravity, and usually negative 9.8, unless we're on another planet, usually negative 9.8, and it's always going to be there. So when I plug into this equation, you can still do the whole copy and paste. The whole copy and paste job. The only thing that's going to change is the time. But be mindful. In this equation, there are 2 times. In this equation, there are 2 times. So generically, how's it going to look? D equals, well, in this case, the V naught is 19.6. 19.6 T plus 1/2 negative 9.8 t squared. Okay. Oh, okay. Can I go ahead and simplify that equation at all? I hope you understand now why I make the times that weird italicize, the italics, I make them italicized, and 1/2 of negative 9.8 is negative 4.9. And the plus signs stay looking like plus signs. But this is why in physics you make your t's in italics so you don't confuse them with a plus sign. Look carefully in this equation. You have one variable, you have two variables. Nothing else is changing. Nothing else is changing. So what we're going to do is we are just going to plug into that equation. D equals 19.6 times 1 plus negative 4.9, 1 squared. D equals 19.6 times 2 plus negative 4.9, 2 squared. The only thing that is changing is the times. Look at it, line by line. The only difference is the time. And once you get it like this, you just type that in your calculator. There is nothing to worry about. Just type these numbers in. That is all you have to do. Notice the initial velocity never changes. Notice half of gravity never changes. That's the essence of what we're dealing with here. And when you type those things in, this is what you get. I actually know this, so I'm not going to type it in. I am intentionally putting the positive signs there just so you know that they're positive. The reason why the displacement is always positive is because if you throw something straight up, that object is always above your hand because it says you're catching it as it returns. So if you throw it up and you catch it, it never goes under your hand. If you think about what's happening in terms of the velocity, it's going up. It's going up when it's positive, hits the top of the path, and then it's coming down. It's going up, hits the top of the path, and then it's coming down. That's what the negative means. The negative is the direction. And we also said, look at the symmetry. When the speeds are the same, the displacements are the same. Look at the symmetry. So there's a lot of things you can do. Some people can get up to this point and they realize, I know the rest. Because I know 0, it's going to be, if this was positive 9 this is negative, negative. And then if this was 14.7, then this had to be 14.7. So there's patterns here. So I want to take a minute and really just examine the two charts. Free fall and vertical throwing. These are the exact two charts that we just made, filled out and placed side by side. Let's just talk about what the differences are. A free fall chart always starts off. A free fall chart always starts off with the double zero. Look at this. The free fall chart always starts off with a double zero. A vertical throwing chart is always going to start off with a 0 displacement, but the initial velocity is going to be the starting velocity. Regardless, once you have your starting velocity, whether it be 0 or whether it be 19.6, to get every other velocity from that point, you just subtract 9.8. 0 minus 9.8 is negative 9.8. 19.6 minus 9.8 is positive 9.8. Regardless of where you start, it doesn't matter. Once you have your starting point, the change in velocity is always going to be the same. The change is always going to be the gravity that transcends the charts. That's going to pull down the velocity in each chart. The only difference is free fall starts from rest, vertical throwing starts with a number. But it doesn't matter where you start. Once you pick that number and you start going down, negative 9.8, 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 negative 9.8. The distance in the free fall chart is actually connected to the displacement of the vertical throwing chart. This is where I'm going to lose some people, and that their heads are going to explode, and they're wondering why they didn't see this before. The distance equation is d equals 1/2 at squared. The displacement equation that we use is d equals v naught t plus 1/2 at squared. Interesting. This 1/2 at squared is exactly the same. And since the gravity is the same, this part of the equation should be the same. So if you know all of these numbers, you could just take the v naught and multiply it by time. You could take the v naught and multiply it by the time, and then add the displacement at that second. What do you mean? Let's look at 1 second. The v naught is 19.6. Remember, v naught doesn't change, times the time. And what is the free fall displacement at 1 second? Minus 4.9. What do you get when you do that? What if I had 19.6 times 2? What is the free fall displacement at 2 seconds? 19.6. When I subtract those, what do I get? The pattern will continue. If you don't get that pattern, that's okay. That's not the most important pattern. You can always use the equations to solve. What I'm more interested in is, do you know how to get the numbers, and do you understand the relationship between them, and do you understand what they're saying? The free fall is always going to be negative because it always goes down below where it starts. The vertical throw, in terms of distance and velocity, this is only speeding up going down. In vertical throwing, the velocity starts positive because it's going up, but what goes up must come down, and then it turns negative as it comes down. The displacement always stays positive because it's always above your hand. However, and I don't want you to get complacent, and I don't want you to think that the charts will always be symmetric. I chose that 19.6 meters per second as the initial velocity very carefully for the other problem because I wanted to have nice, neat numbers. But sometimes you don't have nice, neat numbers, and that's okay. This is a situation of vertical throwing where the initial velocity is 32 meters per second. Because it's vertical throwing, I know that the initial velocity goes in for the velocity at time 0, and the displacement is 0. How will I get these other velocities? Subtract 9.8 every single second. But wait a minute, Bizzuto, you didn't say we were on Earth. It's safe to assume that you are on Earth, even if I don't say it. So minus 9.8. Minus 9.8. minus 9.8 minus 9.8. So this is not a symmetric case. In fact, it's not even the total time it's in the air. It's still going to be coming down because it's going to be coming down all the way until it's going negative 32. And it's not at negative 32 yet, so it's still going down. But that's okay. Even if there are no patterns that we can use to cheat our way through and kind of give us little shortcuts, we know how this works. I know that this ball is going up. And I know that the ball hits the top of its path between 3 and 4 seconds because that's when it stops going up with a positive and starts coming down with a negative. And if I didn't like that 9.8 pattern, of course, I could have used this equation. V equals V naught plus AT because it's vertical throwing. Displacement, however, works the exact same way as the other problems. There's just not going to be a shortcut. There's not going to be a symmetry shortcut. But the V naught is always going to stay the same. The V naught is always going to be 32. And half of negative 9.8 is always going to be negative 4.9. So I hope that if you get a problem like this, you see that equation, you're like, I got this. I'm going to turn it into this. D equals 32 T plus negative 4.9 T squared. And all I'm going to do is just plug in the time. I'm going to plug in the time to both times. Don't forget both times. People forget both times, and it's a problem. But ultimately, when you do that, you should get pretty simple answers. We expect it to be getting bigger because it's still going higher. It's not coming down yet. So we expect it to get bigger. And it does. Why am I not showing all the work? I did right here. All I'm doing is for 1 second, I'm plugging 1 into the T's. For 2 seconds, I'm plugging 2 into the T's. For 3 seconds, I'm plugging 3 into the T's. For 4 seconds, I'm plugging 4 into the T's. It's coming back down. The displacement is a little bit lower. That actually kind of makes sense if you think about it. And I want you to think about it. So, okay. So I've been saying all this time that we are always going to assume that we're on planet Earth unless I tell you otherwise. So let's just say, what if you're not on Earth? What if you're on the moon where gravity is negative 1.6? What changes? Instead of using negative 9.8, we just use negative 1.6. That's the only difference. That's the only difference. It's a free fall. 0, 0, double donut. 0 on a free fall. And now the velocity is going to change by negative 1.6 every single time. Just keep changing by 1.6. If you don't like that, bam. If you use this equation, please know that the 1.6 is now your A. Because we're not on Earth, gravity is not negative 9.8. And the same thing is going to apply for the distance. When you do the distance equation, it's not going to be 1/2 of negative 9.8. It's going to be 1/2 of negative 1.6. So let's plug that in. Let's see what that becomes. 1/2 negative 1.6 t squared d equals, sorry, that's negative 0.8 t squared. That's it. That's it. D equals negative 0.81 squared. And then you're going to do it again, and the only thing you're going to change is the time. Nothing else. Nothing else. So of course that's got to stay squared. I can't fix that. That's all we're doing here, folks. Where did that come from? I just kept adding the times into that equation. When you do these charts, the only thing you change is the time. Okay. Well, what if you did vertical throwing with a different gravity? Well, how's that going to be different? I think you all know. I think you all know. Well, because it's vertical throwing, you know this. We know this. We should know that. That's not in question. How's the velocity going to change every time? It's going to change by gravity. What's the gravity? Is it negative 9.8? Nope, because we're not on Earth. We're on the moon. 15 minus 1.6. I like putting the plus and minus signs. I encourage you to do so. It's going to definitely help you out. And you're just going to keep minusing 1.6 every single time. And again, for those of you who really like the equations, that's great. And this time, the V0 will always be 15. The A will always be negative 1.6. The only thing you change is the time. What about the displacement? Displacement's a bit tricky. Not really. Got to use this equation, sure. But we know how it works now. D equals 15t minus 0.8 t squared. Where did the 0.8 t squared come from? Half of negative 1.6. That's all we're doing. That's all we're doing. And you're going to plug that in every single time. So I wrote it as plus a negative. I'm out of space. Curses, I need more space, but I think you get the idea. Plus a negative or just straight negative. I'll keep it plus a negative just so you can see it. But it does technically turn into subtraction. And then you're just going to keep doing it and replacing the time and replacing the time. And the only difference is that instead of negative 9.8, now we're going to use the gravity of the moon. So of course, this is going to become 14.2. With my calculator, I type it in once and then I just hit second enter and it pops in, and I can move my cursor around and I just change the 1s to 2s and I don't do anything else and I just keep it moving. I have to change both times though. I cannot stress how often students will forget to change both times. They'll just change one of the times. And it's not even consistently which one they changed. But there you go. That's it. Word problems. Something that is always a good deal of fun, but let's see if we can make sense of this. If something is moving through the air on planet Earth, it's safe to assume that gravity is pulling on it. Gravity, of course, is negative 9.8 meters per second squared. So words like dropped or falls, these words indicate a free fall because it starts from rest. If you drop something, it starts from rest. Words like thrown or launched indicates vertical throwing. And of course, if you ever see an initial velocity, well, then you know you have vertical throwing. A ball is dropped for 4 seconds. How fast is it going? Dropped. Free fall. Free fall equations. It doesn't say Earth, but we assume A equals 4. A equals, negative 9.8. T equals 4. How fast is it going? Well, if it's free fall, looking for velocity. There's no initial velocity in free fall. V equals AT. Done. V equals negative 9.8 times 4. V equals negative 39.2 meters per second. Simple. A ball is thrown straight up plus 50 meters. Well, if you're throwing it, it's probably vertical throwing, which means that the V naught is 50. So the V naught is 50. It's thrown straight up into the air. It says how fast is it going? So that means, again, we're looking for velocity. 4 seconds. Feel like we're missing some information. Of course. Of course. Gravity. Because it's vertical throwing, we've got to use a vertical throwing equation. Nice. I just type that in my calculator and I get simple. Vertical throwing versus free fall. We know the equations. They work the same way. Now we've got very similar, but instead of how fast, it's now saying how far. Ball is dropped. That's free fall. So we're looking for distance. Distance is a question mark. Dropped. So we know gravity is what's accelerating it. Don't have to say that. Don't have to say being pulled by gravity. Don't have to say you're on Earth. You assume all of that. You just plug in. You may have seen these numbers before. These are the free fall numbers. They're always the same on Earth. We've seen this. It's not new. Thrown straight up. V naught, it's vertical throwing. Awesome. A is negative 9.8 because we're on planet Earth, of course. When you're looking for the distance, you can go ahead and use the distance equation. Plug in. This is All we're doing is just plugging in. We know what we're doing. We know how to use these equations. When I type all that in my calculator, I think I get 121.6. We cannot forget the processes and the strategies that we learned at the kinematic equations. They will be with us forever. And that's basically it. Gravity pulls on all things in the air. And the fundamental difference between free fall and vertical throwing is the initial velocity. That's it. Gravity still pulls it down. The velocity still changes by the gravity every second's in the air. But if you have an initial velocity, you have to use the initial velocity equations. If you don't, then you don't. Because once an object is in the air, gravity pulls all objects down the same way, regardless if dropped or thrown. That's it. That's the key.